Our next topic in universal circular motion is simple harmonic motion, where there really is a strong connection between those two ideas. But we'll see that later. First of all, what is simple harmonic motion? And the best way to get an understanding of it is to consider examples of it. So consider a vertically vibrating spring mass system, a cart oscillating with springs on a track, and a swinging pendulum. All those in motion are examples of simple harmonic motion. And you will probably have opportunity to see these things. Well, if you observe the motion, so here's the vertically vibrating spring system, the mass is doing this. And over here, it's oscillating back and forth horizontally. And then the swinging pendulum is swinging back and forth. If you consider each of these motions individually or collectively, there's some observations that we can make about their motion. So I'm going to write a sentence here about what simple harmonic motion is, which is motion that repeats itself over the same path, always seeking the equilibrium position. So the equilibrium position for this guy is right here, and it goes up and down about that equilibrium position. Here's the equilibrium position. It goes back and forth, and it always kind of seeks that equilibrium position and then passes through it. Same thing here. Equilibrium position, back and forth through it, not stopping on it, especially if there's no external friction. Now, the type of force that causes simple harmonic motion. A very good example is a spring system. Springs on a mass will cause this type of motion. And it produces what's called the restoring force. Restoring it where? Back to the equilibrium position. If we displace this from the equilibrium, it goes back toward it. When it overshoots, because of inertia, hint hint, it then will start being restored back to that equilibrium position again. So every time we're displaced somewhere other than the equilibrium position, there's a restoring force pushing us back toward that position in each of these situations. Now, if we carefully investigate the nature of that spring force, so we take a spring and hook a scale onto it and pull at a certain distance, we see that the scale reading goes up and up. Well, in what manner does it do that? Well, if we pull it double the distance, we will notice, let's see, maybe goes up by a factor of square root of 2, maybe just doubles, maybe quadruples, an x squared type of function. Well, the real answer is that when we double the stretch, the force doubles as well. So the size of the force is kx. In other words, the force, the spring force, is proportional to x. And k is a spring constant, Hooke's constant, proportionality constant. That depends on the stiffness of the spring. So here it is graphed, force and x. And now I'm also going to put one on the other side, because if you, for instance, are displaced negatively, then that force, the spring force, is back in this direction, toward the right. If you're displaced to the right, the spring force is toward the left. So in any case, at this point here, there's a transition, and the force is in the other direction than it was at first. So that's the idea. Now, the direction of force then is toward the equilibrium. It's always toward the equilibrium. So we can kind of draw that with these arrows. If we're displaced this way, it's this way. If we're displaced negatively, it's toward the positive side. So really, this is the force that causes SHM, and the force is in the opposite direction of the displacement. That's the nature of that restoring force. So it's caused by a negative restoring force, really. So to get technical, there should be a negative in front of this. The spring force is in the opposite direction of the displacement. So we call it a negative restoring force. And if it has this characteristic of being proportional to the force, then it will produce what we call simple harmonic motion. A few more introductory comments and definitions. So we have this mass oscillating back and forth between these positions here, between what we call A and minus A. So those are special locations, the full extent of the swing. So where will the object M be at rest? Well, it's at rest when it comes to a stop, obviously. So that's where x is equal to plus or minus a. And this is what we call the amplitude of the vibration, or the oscillation. So the amplitude is the largest extent of the displacement of the mass. Okay, at what 2 points is the motion the greatest? Now it's moving fastest when the acceleration is done, and that's right here in the center. That's where x is equal to 0, and it's called the equilibrium. Next question is, where is the restoring force the greatest? So the restoring force, the force that tries to make it go back to the equilibrium position. And that's going to be, of course, where the string is most stretched. So that again is plus or minus a, the amplitude. And then where's the acceleration the greatest? Well, you should know that acceleration is directly proportional to force. So of course, it's plus or minus a. All right. A vertically vibrating spring. We have the top, the equilibrium position, and the bottom. Those are the key places, and it oscillates between those two locations, the top and the bottom. So we have the limits of the oscillation here, and x is equal to 0 at the equilibrium, and plus a at the top, minus a at the bottom. Likewise, we can consider a pendulum, and at the bottom, where it's just hanging, x is equal to 0, and then plus or minus a at the maximum extent of the swing itself. So in summary, simple harmonic motion swings through the maximum positions of plus and minus a, the amplitude, where the restoring force is the greatest, least, average. It's the greatest. That force, that restoring force, is always in the direction of the equilibrium position. And at the equilibrium position, it will be moving the fastest. So in the next video, we're going to look in more detail at the particular locations that the SHM object is in and what it's doing. So we're going to actually graph it with respect to time and position.